Hello and welcome to another video. In this video we're going to be going over best meeting point, which is the problem week for this week. And in the problem you're given an n by n binary grid where 1 marks the home of one friend, and you want to return the minimum total travel distance. Total travel distance is the sum of the distance between the houses of the friends and their meeting point, and you calculate it like this. So for example, if this is the meeting point, for every person you add their x distance and their y distance to get it. So like here, if this is the distance, then like this person would have an x distance of 2 and a y distance of 0. This person would have an x distance of 0 and a y distance of 2. And this person would have an x distance of 2 and a y distance of 0. Altogether, we would get 6. So this is the meeting point. And in the second example, if you just have a grid like this, then you just pick one of these two and pretty much the travel distance is 1, right? One of them is going to have to travel and the other one's not. So the tricky part of this problem is the constraints. Now, and I think once you start doing these hard problems, I think a very useful skill is look at the constraints and figure out right away if you're going to get like a TLE. So in here, m and n are 200. So if m and n are 200, something you might consider that would be pretty straightforward if you could do it is you just mark every single point, for example, right? And then you can just say like, okay, well, for each distance, let me just get those points. So you could literally just like, it would be something like for every single meeting location, let's say you try to meet here, you would just get every single one and you would subtract that location, right? So you'd say like, okay, meeting is at 0, 0. Let me just loop through this entire grid, calculate all the distances, and then get that total distance, right? So it'd be like, this would have a distance of 0. You'd keep going, keep going, keep going. This would have a distance of 5. You know, this would have a distance of whatever it is, right? And so essentially this complexity, right, where you just say like, let me just pick every single point as my possibility and let me walk through my entire grid. And then for every one, or even if you don't walk through your entire grid every time, let's say you store these ones in like a dictionary and you just say like, okay, for every single meeting point, let me go through that dictionary and calculate the total distance of every single one of those points. The problem is you can have a ton of ones here, so like half the grid can be ones. And then essentially you're going to have an m by n times m by n complexity, right? Because for every single possible location that you try, which will be m by n locations, you'll have to look at all the ones, which are also going to be m by n, like I said, if ones are like half the grid. So you can't do something like that, and that would be kind of like the easy solution. Maybe it would be like a medium problem if that worked. So that doesn't work. So it's actually pretty tricky to find out the solution on how to do this, because essentially we need something like m by n by like a log or something, right? Like, or m by n by m, like one of the dimensions would pass. And how would we do that, right? And that's kind of the tricky part here. So something like, essentially you can't have four m by n. So like this would pass, something like that would pass, or like one of the dimensions, or just m by n overall, you know, like any one of those would be fine. So the way we're going to do this is we're going to actually go through one row and really try a bunch of different things and then really figure out like where is an optimal meeting point. And then we're going to draw conclusions from there and apply it to the whole grid. And kind of if you do this problem, there's a hint they give you, like try to do this for a row. So let's do that. So just say we take this row here. And we're just going to put in some ones and some zeros. So let's just say like there's a 1 here, 0. So we get a little bit better. 1, 0, 1, 0, 0. Something like this. We can even actually probably get rid of some of these because we don't need this many cells. So let's just get rid of it and make it like a few plus. It's good enough. All right, let's do 6. There we go. We don't need that many. So for something like this, or let's start with something really easy. Like let's start with something like this. You might think, okay, well, the optimal meeting point is going to be like here or here, right? It just kind of like, you see like that's the middle. And in reality, it's actually doesn't really matter where you meet. So let's just look at this. So let's say we meet like, right, like one of these two places. What would be our distance? So here, our distance from the left is 2 and our distance from the right is 3. So here we have a distance of 5. Let's check this point. Here we have 2, 3, distance of 5. But what about if we just pick something like this? we have 1, 2, 3, 4, and 1. So we have a distance of 5. And here we have a distance of 5. And actually here we have a distance of 5 because one person has to travel 5, and then the other one doesn't have to travel at all. So if you just have these two numbers, you might think like, let's meet in the middle, but actually all of these work. So now let's change this a little bit. Let's say we have like this. So from the logic from before, when you had 2, it didn't really matter where you meet. Well, now you probably want to meet, like out of every point, where would you want to meet? Well, now that you have a third person, you probably want to meet at the third person because then the third person doesn't have to move. So this is actually the best, and we can take a look and actually calculate distances here. So here we have a distance of this person would have to move 2, this person would have to move 1, 2, 3, 4, 5, so we have 7. Here, this person would have to move 1 and 1, and this person would have to move 4, so 6. Here we have 2 plus 3, so we have 5. Here we have 1, 2, 3, 4, 5, 6. Here we have 1, 2, 1, 2, 3, 4, so 6, I think 7. Hopefully I did that correctly. Let me just double check. 2, 1, 2, 3, 4, 6. Yeah, I think so. And this one is 1, 1, 2, 3. Yeah, I think this is correct. And here this is 1, 2, 3, and 1, 2, 3, 4, 5, 8. So you can see that like when you have 3, the best place to meet is the middle. And if you do enough of these, you will kind of realize that essentially, if you have an odd number, it doesn't really matter which way. Like we can even do something like this. Like this. The best place to meet will still be the middle guy, because as we noticed before, when it was this, remember it didn't really matter, right, where we met. So now if we add a 1 here, it makes sense to meet at that middle one because that person would have to travel 0. So we could like do this whole thing again, but you will notice that the best thing to meet is at here. And if you actually had ones all over the place, like let's say you had a 1 here and a 1 here, let's do 1. Or actually, let's not make it symmetrical. Let's make it like this. And you'll see it actually doesn't matter. So you can see this isn't symmetrical. So you might think like it doesn't, like where do I meet? So actually, if you just calculate this for all of these, the best places to meet would be here and here. So it's always going to be either the middle one if you have an odd, or it's going to be one of the middle two. So if we actually calculate this, let's do this really quick. So this person moves 1, 3, and then 4, 5, 6, 7. So we have a 7 here. Then this one is this person moves 2, this person moves 3, so 5, and then 7 again. And everything else would be further. So that's kind of the general rule for here, and you have to kind of play around with it enough to do that. So we can write this down. So for odd number of ones, meet at middle. For even, meet at one of the 2 middle ones. Doesn't matter which ones. Now, we really want to be able to figure out where to meet without actually, like, if you notice, we don't really need to store the zeros. Like, what if we just stored, instead of doing this, what if we just stored every number and its index? And that's kind of what we're going to do. So essentially, like for this, we'll just store like, and let's write down the indices here. And let's get rid of these. So if we just store like 0, 1, 2, 3, like this, right? What we're going to do is we're going to have a hash map of a row, and if it has a 1 or a 0, we're just going to show the one-dimensional one first. So we'll say like row 0, row 0 will have 1, row 1 will have 1, and we're not going to include any rows at all that have zeros because we don't really care. Like we're never going to meet at a 0, we're always going to meet at a 1. So row 3, 1, row 5, 1. Now we can just like get the sum of the values, and we know the sum is 4. So if the sum is even, remember we have to meet at one of the middle ones. So what's the middle one? It's going to be 2 or 3. So let's just say we meet at let's just say we meet at 3 for our generic case. So we can just like go through these values, and we're going to have these keys in order, because the nice thing is a Python dictionary, we're going to put these things in order, right? We're going to go like column by column. So this will be in order. And we're going to say like, okay, we'll have a total. And when our total reaches 3, or like when our total encompasses 3, I guess in this case, it's only by 1. So when our total is 3, that's the one we want to have. So like we'll go through this one, we'll have a total of 1. We'll go through this one, we'll have a total of 2, 3, and we'll say, okay, this is the one we're going to meet at. And this would also work for odd. So notice if we just add like another one here, So now if we change this to, we add another item. So let's do that. Let's move this 0 over here. I probably should know. That's fine. Okay, so 2 will have a 1, 1 will have a 1, and 0 will have a 1. And then what we need to do is we can do the same thing, right? So we can say, like, where do we want to meet? Well, it's odd. So if we have 5, we want to meet at the middle one. So we just like 5 over 2. And you can just round this up, right? So you take whatever number you have over 2 and round up. So we'd round up to 3. And if we had 6 over 2, we could meet at 3 or 4. So we would just meet at 4. So we can just like divide and then do a ceiling there. So we could say, like, when our sum is 3, we'll just go down our keys, add it up. So we have like 1, 2, 3, and this is the place we want to meet. And this would be the best place to meet if you do this whole calculation again. You're going to want to meet, if you have an odd number, you're going to want to meet. And it makes sense if you think about it logically. Like, let's say you are at this middle point. What happens is if you move left, every single number to the right of it, the distance will add 1. And then every single number to the left of it, you will remove 1, right? But when you move left, you will also add 1 here. So you will add 1 to these 3, and then you will remove 1 from these 2. So ideally, when you shift it, everything to the left gets like if you have it here, let's say, and you try to move it over here, then same kind of thing. All of these will add 1 to the distance, and all of these will subtract 1. And because you're subtracting 1 from 3 numbers and adding 1 to 2 numbers, that's better. So that's kind of a more intuitive way to think of it, is you want to put your thing, where there's an even number of 1s on both sides. Okay, so that's kind of how we do it for a 1 by 1. Now let's add a little complexity, and let's actually add another row. So we can just copy this. Hopefully this works. There we go. Put it over here. Now we're going to put numbers all over the place again. And this is where it gets tricky and a little bit unintuitive. So let's say we just have some random stuff like this. So like we realized to meet here, but what if we have a bunch of rows? And if you think about it, this is basically the same thing as these things now have weight, right? So this has like 1, this has 2, this has 1, this has 2, and so on. So we can actually write it out as a sum. So we can say like, okay, for the totals, we can just say like this has a total of 1, total of 2, total of 1, total of 2, total of 0, total of 2. So now this has weights. All these ones have weights. Once again, we don't really care about any row with 0, so it's going to be the same thing. So now what we're going to store is we're going to store it in this format. So instead of storing just 1, we're going to store the same dictionary, but we're going to store a total. So we'll have row 0 will have a total of 1, row 1 will have a total of 2, row 2 will have a total of 1, row 3 will have a total of 2. And this is just to get the x distance, right? Because the Manhattan distance, if you look, the x and y are mutually exclusive. So like we can just figure out like what's the best x location, and then we could figure out what's the best y location. So the y location would be kind of the same thing, except the x you're going through the columns, and the y you would go through the rows, and it would be the same exact thing. So let's do this total. So for 4, remember we don't care about any total with 0. So for 5 we have 2. Now it's kind of the same thing. We are going to want to meet at a median, and if this doesn't make sense to you, you can just kind of write out the index of this. So you can have like, let's say this will be like index 0, index 1, index 1, index 2, index 3, index 3, index 5, index 5. And you'll be like, okay, what's the median location? So we have 4 here and 4 here. So it's going to be at either index 2 or 3. And let's double check here and kind of do this total thing. So if we do a total, again, we will have a total of 3, 7, 8. So we'll have 8 items. So that means we can meet at either 4 or 5. Remember, we're going to always choose a higher one because that way it would also work for the odd number. Because if we had 7, we're going to want to meet at 4. So you can meet at 4 or 5, but we're going to pick the higher one. So let's check where we have a total of 5. So we're going to have 1, 3, 4. Now we have a 6. And so this total, as soon as we hit a total that's bigger or equal to the value, that's going to be the thing here, right? Because this 6, that means it has the 5 and the 6, right? Like, this has the 4, this has the 5 and the 6, and so it encompasses it. So that's kind of like, we will just keep adding the value, and then the first one that gets over the total, that means that column encompassed it, right? So it's going to be this column over here, and we noticed before that was one of the valid columns, right? Because we wanted 4 or 5, which was when we did this kind of thing, we saw it was this, right? 2 or 3. So 4, and if notice if we picked 4, so this would have 6. If we picked 4, then it would be this column, which would be 2. So that's kind of the idea, is you sum up the values for each. So when you want to get the x value, you sum up the values for each column, right? So you sum up the values for each column. We can write that down as well. X, sum up values for each column and meet at median. And then y, it's going to be kind of the same thing, except now you sum up the values for each row, because we're trying to figure out like where we would want to go this way, right? So we sum up the values for each row, and then we would meet that way. So let's say this had, you know, if let's say our row values were like 4, 5, 6, 4, 2 or something, we do kind of the same thing where we would figure out like what's the median, and then we're going to have these same keys. So what we're going to do is we're going to have two things. We're going to have a column sums, which will be this one, right? And then we'll have a row sums. And basically what's going to happen here is we're just going to go through these things, figure out like where does the median need to be, and then how do we get it? And so now the nice thing about having these column sums and row sums, the alternative you could do, and it will totally work, is instead of doing these dictionaries, you could just take every single one and you could like put it in an array, right? So you can take every single one and put its index in an array, kind of like I did here, and then get the median. And that would totally work. Like, so for example, for your median x, you would make an array of all the rows for every single one, and then you just figure out like where's the middle. That would totally work, but the problem is, so this would actually pass on LeetCode as well, but that would be m by n, because you can maximally have like the entire matrix, where now if we store the sums, it's actually m plus n, so it's like a small optimization. And I did notice once you do enough hard problems, you're really going to get better at making these optimizations. It's going to be a lot clearer, like, oh, I don't need this, I can make this faster, I can make this faster. Even though like at first the solution was kind of hard, maybe you didn't get it. Once you kind of get into the swing of things, you're going to start to see these optimizations as you do more and more of these problems. But that's the idea. So we're going to get like an optimal row and an optimal column just by getting the median for both and figuring out like we're just going to keep adding to we're going to have a dictionary of column sums and row sums. And when we get a median for the x, we're going to go through the column sums, figure out like what column does that need to be in. And then the same thing for the row sums. When we get the median for y, we're going to go through the rows, figure out where that needs to be. Then once we get an index, it's pretty straightforward. So like let's say we determined the index was here. Then it's pretty straightforward. We can just pass through here, and now we can calculate the Manhattan distance for every single one, right? So we'll say like, okay, for every one we encounter, what's the Manhattan distance to this point? How about this one to this point? How about this one to this point? Because we only have to check one point, right? We're going to get a point, and then that is going to, so we're not going to check every single point. We're going to know exactly what the best point is, but then we just need to calculate this distance. So that's kind of the idea. And then we are also going to traverse this graph twice in the beginning because I don't want to sort the keys. I want the columns to be in sorted order. So in order to have the columns be in sorted order, what you're going to want to do is for every row, you're going to want to go through the columns like first, right? So you're going to want to go like row by row. You want to go from the start column to the end column like this. That way, when a column has a value, you will get it first. Actually, I think what you want to do, scratch that. I think if you want to get a column total, instead what you want to do is instead of going like this, you want to go through the column, right? So in order to get a column total, instead of going row by row, because let's say this had a 1, this had a 0, and let's say this had a 1. Now this would be problematic, right? Because what would happen is you would be like, you'd go row by row and be like, okay, this is column 4. Perfect, column 4 has a 1, but then you'd come here and then you'd have a column 3, so your columns wouldn't be sorted. So the better way to do that, if you want a column total, is you go one column, then you're guaranteed to get it, then next column, the next column, the next column, the next column. And Python, when you insert keys, they will be sorted. You could also just insert the keys yourself. You could just insert all keys, or like you can make an array and that would guarantee you sorting. But because I'm not including any rows or columns with zeros, it's going to work better like that for me. So you could, like I said, you could do, that's up to you. So yeah, you could have an array or whatever. And then when you want to get the total for the rows, it's going to be the same thing. So we're going to go through row 0 like this, then row 1, then row 2, right? So we're going to do two nested for loops to get all our keys in order, get a point, and then we are going to calculate the Manhattan distance for everything. So let's take a look at the code for this because this video is getting kind of long and there's a lot of code. So let's full screen. So we're going to, first of all, get the rows and columns, right? And then, like I said, we're going to get a row sums and a column sums, right? And to get the row sums, you want to go through the row, like row, you want to go through each row, like through the whole row. And then to get the column sums, you want to go through the columns. So you basically swap these around. That way your keys are always in order. Then we just calculate a median. Like I said, you just take all the values, add them all together. So let's say you had like 26 ones. You knew that like, okay, I have to be at one number 13 or 14, and I'm just going to pick the higher one, so I'll say 14. So you get those, the rows and the columns. And then you have basically the same code twice. Essentially what it does is you go through the keys and you figure out where the value lies, right? So what's going to happen is you're going to have a row median, for example. So for a row median, you're going to go through your keys for the row, and you're going to say, I'm going to keep adding the current for the key, like I showed in this picture, right? So let's say our median is whatever, like 7. We're going to say, let's have a current. Let's keep adding these keys. And then when the total is greater than or equal to 7, that's the row or the column that we want. And that's essentially what we're doing here. So we start with a total of 0, and we just keep adding until we eclipse the row median. And the first item to eclipse the row median has to have the row median in it. So once we get it, we break, and otherwise we just keep adding the value and keep going. Then we actually have this optimal location, right? So we have a row result and a column result, and that's going to be like the location we want to be at. Then we loop through one more time, and we just calculate Manhattan distance. So that part's pretty straightforward. You just say like, if we have a 1, let's calculate the Manhattan distance to our optimal point, and then let's return the result. And so let's go through the time and space. And I did look at the editorial for this one actually, and I think we actually beat the space for the editorial. And the time is the same. You can't really do better than n by n. So but it's n by n, but let's go through y and things like that. So this is n by n, obviously, right? Nested for loop, n by n, n by n. This part is worst case. This is O of, so if row is m and column is n, this is m plus n. And then going through the keys and values in a row is m. And then going through the keys and values in a column is n. So this is like m plus n again. And this is m by n. So we have a bunch of m by n's, and we have some m plus n, so it rounds up to m by n. Now, like I said, the nice thing is we're not storing every single one in here. We are only storing the totals. This is very similar to the problems of the day that I did in the last few days, where we did these like column row totals, because this is just like a significantly harder version of something that uses that. And I think I did a few other problems that were like super hard that uses other optimization. But except for that one, you actually needed it to pass. This one, you don't need it to pass. But sometimes you will, like let's say your constraints are, instead of whatever it was, you have to have like m by n times m plus n instead of m by n. That can happen for like very hard problems. They will give you constraints where your stuff barely passes if you have the optimal solution. So that is something you can do. Anyway, so let's go through this. So row sums, for every row, we will have a total. So this is O of m. This is O of n for our storage. These are O of 1, O of 1. So essentially, we are storing for the row sums and column sums, this is m plus n. And we can run this. So I think because like you can probably optimize the number of times you run these loops. I notice everyone's code is roughly in this like little thing, but you notice our space is really good. Because we have like an m plus n solution, and most people have m by n or worse. So you can probably do this in less loops. That's the other thing is like, you can look at people's code and you can see roughly where it is, and you can see like everyone's code is roughly in the same vicinity. So like, let's say our stuff was like 116, but then you get some other person like 36. That means they probably use a different solution or a better solution. But this just means like you just run it a few times and it falls all over the place, right? So it's not really significant. Like I think I ran it before. It was here, and so on. So if you look at something like this, yeah, they're essentially, this is an m by n space, but there's less loops, so that's why it's faster. So it's kind of like trade-offs. But the time complexity can't really be better than this. Yeah, so that's going to be all for this one. So hopefully you like this one. I thought this was a really interesting problem. And it was pretty difficult, to be honest. Like, like I said, if the BFS if like just manually trying every single cell passed and compared to everyone's, obviously that'd be like a medium problem. But figuring out like, okay, where do I actually want to be in the center? And then how do I do this with multiple rows is definitely pretty tricky and something very rare that I haven't seen before. But now that I have seen it, like you can definitely see problems like this, and if you see something similar, you can definitely apply it. Yeah, so hopefully this is helpful. Pretty nice problem. And if it was, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.